Hello and welcome to Snow Day Lesson 1. Our topic today is thermodynamics. We're going to talk about heat and energy. Specifically, our objectives are first for you to understand the difference between heat and temperature because we tend to use them interchangeably. We're going to talk more in detail about the law of conservation of energy and how when we lose mechanical energy like kinetic and potential energy, we can generate thermal energy. We're going to define what thermal energy is, and we're going to look at how do we calculate temperature changes in solids and liquids when heat flows into or out of a system by using formulas that include specific heat. So first, let's review conservation of energy. Remember that last semester we talked about the fact that total energy of a system is constant. It just gets converted from one form to another. Our forms of mechanical energy, kinetic, gravitational, potential energy, spring, potential energy, those are our mechanical energies. They can interconvert, but in the presence of a force like friction, we lose mechanical energy and we generate thermal energy, right? Friction results in rubbing, which generates thermal energy. And the total energy of a system, which consists of these forms of mechanical energy, thermal energy, chemical energy, nuclear energy, is all constant. Now, we didn't talk at all about thermal energy last semester, so first let's define what thermal energy is. Thermal energy is the energy of the atoms or molecules in a system. It is the combination of the kinetic energy, right? All the molecules, whether it's a solid, liquid, or gas, are in motion. There's potential energy in those atoms and molecules through the bonds between molecules and the interactions between atoms and molecules. Forces of attraction, intermolecular forces result in potential energy. So all of these energies are the thermal energy contained in a system. Now, energy can be transferred into or out of a system via work or heat. Last semester we talked about how we could do work on a system and that would increase the energy, right? We apply a force to an object, we move it, and it changes its kinetic energy. Or a force could do negative work, right, like friction, and reduce the amount of mechanical energy in our system. We never talked about heat, although it was on our diagram that we looked at last semester. But heat can also transfer energy into or out of a system. Now, before we talk more specifically about heat transfers, we need to understand the difference between heat and temperature. Heat and temperature are related to each other, right? I can transfer heat into a system and change its temperature, but they are not the same thing. What temperature is something we can measure, right? We have thermometers, we can measure temperature, but what we're actually measuring is the average kinetic energy of the molecules in the substance. The faster they're moving, the more kinetic energy they have, the higher their temperature is. So temperature is called a state function. It's something we can measure. Heat is actually an energy transfer. It's a process. So if, for example, I use electrical energy to turn on this hot plate, and what's going to happen is I'm going to generate thermal energy on this heating coil through friction, and if I put a beaker of water on it and say I measure the water at room temperature, it's about 24 degrees Celsius. As the heat is transferred from that heating coil to the beaker to the water, all right, that will result in a temperature change of the water. So heat is the transfer of energy, right? That energy goes into increasing the kinetic energy of the molecules in the water, and therefore the temperature will increase. Now, I don't want you to confuse heat and temperature because we're used to heat being transferred in and temperature goes up. But we will see when we start talking about gases that we could transfer energy into a system and its temperature might not change. It depends upon what's going on with work, because work and heat will work together or against each other in changing the energy of a system. Let's talk some about the energy of systems. So we know that kinetic energy, if there's friction, right, will result in a loss in mechanical energy, a loss of that kinetic energy, because we begin to generate heat. This was something that was studied by a man named James Joule. And in 1850, James Joule determined the mechanical equivalent of heat using an apparatus that looks like this. What he did is he took a weight of known mass and hung it a known height and attached it over a pulley and a spindle here, which was attached to some paddles that were in an insulated container containing water with a known mass. And he dropped that weight many times, and he observed that the temperature of the water increased. So through the loss of the potential energy of this weight, converting that into the kinetic energy of the paddles, he found that this kinetic energy of the paddles would be transferred into a gain in temperature in the liquid. So the loss of potential energy, he found, was equal to the heat transferred into the liquid, which resulted in a temperature change, which was proportional to a temperature change in the water. Now, the heat did not equal the temperature change because heat and temperature are not the same. How they're related in solids and liquids is through this formula, which you should remember from chemistry. Q is equal to mc delta T, or I call it Q is equal to mcat. Now what Q is that heat. The heat that was generated through the loss of mechanical energy from the weight falling. M was the mass of the substance, so in his case the water. C is the specific heat of the material. Each material has a specific heat. It is a property of a substance. It's something you can look up in your physics book or in a book on constants, or you can Google specific heats. And of course, delta T is the change in temperature, final minus initial. Right? If the temperature increases, so your final temperature is greater, that results in a positive value of Q. Heat is transferred into the system. If the temperature drops, your final temperature is less, right? That results in a negative Q, which means heat is transferred out of the system. What this tells us that the relationship between heat and temperature is affected by the mass of the substance. Whether I place a large beaker of water on this hot plate or a small beaker and I turn on my hot plate, the temperature change is going to be greater for the same amount of heat flow if I have a smaller mass, right? So higher mass requires more heat to change the temperature by the same amount. Specific heat is also important into determining how much heat I have to put in order to change the temperature. Like I said, specific heat is a property of a material. It's defined as the quantity of heat required to raise 1 kilogram of a substance by 1 degree Celsius. I should say Celsius. Now, if we take a look at a couple different materials, here's lead, right? Lead is a metal. Here's glass. There's aluminum. Aluminum also a metal. And I heat each of these substances. I apply heat and I transfer heat in to increase their temperatures to 100 degrees. What we would find is that the lead doesn't take very long to heat to 100 degrees, whereas the aluminum takes 60 seconds, so a longer period of time. What that means then, if we think about which has the greatest specific heat, well, the one with the higher specific heat requires more heat to raise 1 kilogram 1 degree. In fact, here is a table from the book. We can find here lead, which doesn't take very long to increase in temperature. It has a specific heat of 130 joules per kilogram degree C. We will work in joules, not in kilocalories. Whereas glass has a specific heat of 840, and our aluminum has a higher specific heat of 900. So therefore, it should make sense to you that higher specific heat requires more heat transfer in order to raise the temperature by the same amount. Now, if we look at our table, you can see that, except for aluminum, most of the metals have very low specific heats. right? Lead 130, iron 450, copper 390. That's why when you cook in your kitchen, you use metal pans. Metal pans require less heat transfer to change the temperature, so that means you can heat your food faster. You wouldn't want to heat your food in wood. Wood, well, besides the fact that wood might start a fire because it's combustible, it would take a lot longer to cook. Now, the thing that takes the longest to increase in temperature is water. Water has a very high specific heat. So of all the substances here, you can see water, liquid water has a specific heat of 4,186 joules per kilogram degrees Celsius. Very high specific heat, which is great environmentally. Right? So if you live by the coast where you have a large body of water, the temperature change is not as dramatic because it takes a lot longer for water to heat up and cool down. And that's why if you go to the beach in the summer, right, the sand, which has a low specific heat compared to water, gets hot fast. So you need to run across the sand in order to get to the water or your feet burn. As an example of the difference between heat and temperature, I have two materials here, the black squares in front of you, that are displaying the same temperature, both 21 degrees Celsius. Now, to the touch, the material on the right here, which is made of aluminum, feels colder than the material here on your left, which is a foam plastic block. These materials have different specific heats or heat capacities. What I'm going to do is put two ice cubes, or an ice cube on each of the materials, and we are going to watch what happens to the ice cube. All right, so we have an ice cube on both materials. You can see that the ice cube on the aluminum over here is melting much quicker than the ice cube here on the left. You can also see that the temperature of the material is changing as that ice cube melts. Now, both of these ice cubes were similar in mass when I placed them on the foam blocks. And of course, we're both at 0 degrees Celsius. However, the ice cube on the aluminum melts quicker, meaning that there is a heat transfer, a greater rate of heat transfer occurring between the ice cube and the aluminum, as opposed to the ice cube on the plastic foam block, which is almost not transferring any heat whatsoever. When heat transfers between a solid and a liquid, temperature changes, and we can see that very greatly with the aluminum block, which is now registering a temperature of 15 degrees. And the ice cube is almost completely melted on the aluminum block. Now we're going to take a look at these changes in temperature with solids and liquids and how we can calculate either temperature change or the amount of heat flow. So here's an example problem. We have a 3 kilogram iron block. The specific heat of iron is here, 450 joules per kilogram degrees Celsius. It's dropped from the top of a very tall building. It starts with 20 kilojoules of potential energy. When it strikes the ground, it stops, and all of that mechanical energy is converted into heat in the block. Of course, in reality, some will get transferred into heat into the concrete or whatever substance it fell on, but in this example, we're going to say it all gets transferred into thermal energy in the block. How much does the temperature increase? Well, we start out with 20 kilojoules of potential energy. All right, so our potential energy is 20,000 joules. Pay attention to units. Our specific heat is joules per kilogram Celsius. Now, of course, as that falls, all of that mechanical energy in the absence of air resistance is converted into kinetic energy. So when it hits the ground, all of that potential energy is kinetic energy, and then all of that kinetic energy is converted into heat. By our equation, right, Q is equal to mc delta T. It tells us that our value of heat is 20,000 joules. In the problem, our mass is 3 kilograms. We have a specific heat of 450, and what we're trying to find is how much does the temperature increase by. So if we take 20,000 and divide by 3 and 450, we will find that the temperature increases by 14.8 degrees Celsius. Here is another problem, very similar problem. In this case, we're going to drop our 3 kilogram block of iron from the top of some unknown building or cliff. When the block hits the ground, the temperature of the block increases by only half a degree. Must not be as high as our last building was. Assume that all of the potential energy is used to heat the block. How high is the cliff? Well, again, we're starting out with that same formula, and we're saying that all of the heat generated in the block, which goes to changing its temperature, is coming from all of the initial potential energy of the block. So our potential energy equation from last semester, remember potential energy is mgh, and our Q is mc delta T, mcat. So if you'll notice, actually, the masses in this equation cancel, right? There are m's on both sides, we divide by our m's and they're gone. So my equation here for height then, once we move our mg over here, we get c times delta T over g, right? Our m's cancel. And so when I plug in my numbers, 450 joules per kilogram degree C times the change in temperature, which is 0.5 degrees, and we divide by the acceleration due to gravity, which is 9.8 meters per second squared, we will get 23 meters high. So not quite as high as obviously our last building, where our temperature change was 14.8 degrees. And in fact, we could go back and figure out how high that building was, right? Because we know that it was 20,000 kilojoules, or sorry, 20 kilojoules of potential energy. Another example, we don't just have to lose potential energy, drop an object, and generate thermal energy. We could take kinetic energy of a substance and generate thermal energy. So, for example, a 100-gram lead bullet traveling at 300 meters per second, really quick, but bullets are tiny, is stopped by a large tree. Half of the kinetic energy of the bullet is transformed into heat energy and remains with the bullet, while the other half is transmitted into the tree. What is the increase in the temperature of the bullet? Well, first thing we have to do is we have to figure out how much heat energy is generated. So the heat energy is coming from the kinetic energy of the bullet. Well, remember, kinetic energy, the equation is 1/2 mv squared. Now, the heat that is being generated by the bullet is only half of the kinetic energy, right? Because some of the kinetic energy is actually going into the tree, or some of that heat is being generated in the tree itself. So we need to take the kinetic energy, 1/2 mv squared, of our bullet and divide that by 2. Now, kinetic energy is, the equation for kinetic energy is 1/2 mv squared. Our equation for heat, right, is mc delta T. So for Q, I'm going to plug in mc delta T, and for kinetic energy, right, the kinetic energy would be 1/2 m delta v squared divided by 2. Now, the change in speed, right, final minus initial, we are going to have a final kinetic energy of 0, right, it stops. So our only kinetic energy here that we're worried about is the initial kinetic energy. Now once again, you can see that our m's, we have m's on both sides. So when we go to solve this for the increase in temperature, we're going to end up getting rid of the masses. So if I solve this for delta T, right, delta T, if I distribute that half, right, I get mv squared divided by 4, right, we bring that 2 down there, and I'm going to divide that by m and c. So you can see here that our m's cancel. So therefore, delta T is equal to our initial velocity squared, which is that 300, and that's divided by 4 times the specific heat of lead, which is 130. So 300 squared divided by 4 and divide that by 130, and you will get an answer, which I will calculate. So 300 squared divided by 4 divided by 130 is going to give us 173 degrees Celsius. Ouch! Don't touch that bullet. Now, had we left mass in there, remember that you need to work in kilograms. So this wouldn't be 100 in here for m, it would be 0.1. So anytime you find a problem where we have a solid, usually a solid, it's not typically liquid problems, where we are losing mechanical energy and we're generating heat energy, then what you're going to do is find out how much of that energy did I have originally. That is either mgh or it's 1/2 mv squared, whether it's potential or kinetic. And if the object loses all of that mechanical energy to heat, or some fraction of it to heat, then that is going to be equal to mc delta T. So then it's just a matter of plugging and chugging. Thank you for watching our first video. Our next video continues more with heat transfer.